picture this for a second. You're cruising down the highway in a brand new, just state-of-the-art electric vehicle.
Oh, yeah.
And the ride is perfectly smooth, the acceleration is flawless, everything feels entirely under your command.
Right.
But what you can't see is that deep inside the microchips controlling that electric motor, a tiny high-energy particle from outer space, like a literal cosmic ray, just slammed into the system's memory.
Mm-hmm.
Or maybe an intense local spike of heat just warped the microscopic structure of the silicon itself.
Yeah, just degraded it.
Exactly.
Yeah.
And suddenly, in a fraction of a millisecond, the computer completely forgets where the physical parts of the motor actually are.
Right. It just loses its mathematical map of physical reality, basically.
Yeah.
So the magnetic fields that are generated by the inverter, they're suddenly pointing in the wrong direction.
Oh, wow.
So instead of driving the motor forward, it's pushing violently against the motor's rotation.
Which is just a staggering scenario to think about when you're doing,
Yeah.
70 miles an hour.
Well, totally.
And today, we are going to look at exactly how modern engineering prevents that nightmare from happening. We're doing a deep dive into a highly technical engineering specification document detailing calibration data error diagnostics and safety protection for motor drive systems.
Yeah, and specifically, we're focusing on dual motor control systems here.
Right.
And, this document outlines the architectural requirements they need to hit an ASIL D safety target.
Which is Automotive Safety Integrity Level D.
Exactly. It's the absolute highest, most stringent safety classification possible in the automotive industry.
Wow.
I mean, it dictates a system where a failure could literally lead to life-threatening situations, so the fault tolerance has to be virtually absolute.
Which is wild. So our mission today is to unpack these invisible wars happening inside the microchips of modern EVs and to really understand the extreme, almost unbelievable level of engineered paranoia required to achieve that ASIL D rating.
Okay.
So let's unpack this. Because before we look at how the engineers build the defenses, we have to understand the specific microscopic forces that are actively trying to destroy the system's calibration data.
Yeah, and I mean, calibration data truly is the lifeblood of motor control.
Right.
We're talking about parameters like resolver offset angles, which basically tell the computer the exact, sub-degree physical position of the spinning rotor.
Okay, so it knows exactly where everything is.
Right. And we're also talking about current sensor gains, which calibrate the massive electrical flow going through the system.
Gotcha.
If this specific data gets corrupted, the motor's mathematical model of the real world just breaks down entirely.
Wow.
And, the first environmental force trying to break that model is severe thermal stress.
Yeah. Yeah, and the document mentions a specific failure mode here called Fowler-Nordheim charge loss, which, it sounds incredibly sci-fi.
It does.
But this is a deeply physical problem regarding how data is actually stored, right?
It is, yeah. It's literally a quantum mechanical reality.
Okay.
So the calibration data is stored in the microcontroller's data flash memory. And for anyone familiar with flash architecture, it relies on this grid of floating gates.
Right, these tiny little traps.
Exactly, microscopic structures designed to trap electrons. And the presence or absence of those trapped electrons is what dictates your digital ones and zeros.
Okay, that makes sense.
But to keep them trapped, the gates are surrounded by an insulating layer of silicon dioxide.
Right, but the environment inside a high-performance EV motor controller is just, it's hostile.
Oh, incredibly hostile.
Because the specifications note it swings from, negative 40 degrees Celsius in the dead of winter up to positive 125 degrees Celsius under heavy load.
Yeah. And that thermal cycling is just brutal on materials.
I can imagine.
Under that extreme alternating heat stress, the silicon dioxide insulation literally physically degrades.
Really?
Yeah, the microscopic crystal lattice of the insulator just begins to break down.
Wow.
Because of thermal emission at those high temperatures, the trapped electrons gain enough kinetic energy to literally tunnel through or just jump over the degrading energy barrier.
So if we look at this structurally, it is basically like stressing a concrete retaining wall with extreme temperature swings until little microfissures form.
Yes.
And eventually, the water behind the wall finds a path and just seeps through, right?
Yeah.
Trying to keep water in a bucket made of wax while baking it in an oven.
That captures the mechanics perfectly. The data literally leaks away over time.
That is insane.
Right. And the engineers classify this as a multi-bit hard error.
Hmm.
So the calibration values don't just shift a little, the fundamental memory structure fails to hold its state.
Wow.
But thermal fatigue is a slow creeping enemy, you know? The system also has to defend against instantaneous, completely unpredictable strikes from space weather.
Okay, so you're referring to the cosmic rays I mentioned in the intro.
Yeah, and what's fascinating here is that the specification doesn't just worry about high-energy neutrons cascading down from the upper atmosphere.
Right.
It explicitly details the threat of alpha particles being emitted by the microchip's own packaging materials.
Okay, wait, let me push back on that.
Sure.
You're saying the plastic and epoxy packaging surrounding the silicon chip is emitting radiation that causes the computer to crash.
Yeah.
How does a system defend against an enemy that's embedded in its own physical casing? Like, how do you even begin to fight back against something that small?
I know, it sounds crazy. It is an incredibly nuanced material science problem.
Yeah.
Trace radioactive isotopes naturally exist in the raw materials used to make epoxy resins.
Oh, wow.
And as these isotopes decay, they fire off alpha particles.
Okay.
When an alpha particle, or an atmospheric neutron for that matter, crashes into the system's SRAM, which is the high-speed volatile memory where the processor does its active computations.
Right, the working memory.
Exactly. It deposits a dense track of electron-hole pairs. It just leaves a tiny burst of ionizing electrical charge right in its wake.
And SRAM memory cells rely on very specific, delicate voltage states to hold a 1 or a 0.
Precisely. Every memory cell has what is called a critical charge limit, or Q-crit.
Q-crit, okay.
If that transient ionizing charge from the particle strike exceeds the cell's Q-crit, it literally flips the state of the transistor. It forces a single event upset, a bit flip.
So the computer pulls the pristine calibration data from the flash memory into the SRAM to actively run the motor algorithm.
Right.
And in that microsecond, a particle hits the SRAM, flips a single bit, and the control algorithm is suddenly feeding a physically impossible calibration value to the inverter.
Yeah. The motor instantaneously receives coordinates that just don't match physical reality.
That is terrifying.
It really is.
So,
Now, combining heat degrading the flash and radiation scrambling the active RAM, the system is already fighting on two quantum fronts.
right.
But it also faces macroscopic brute force electrical realities. Specifically, power sags resulting in what the document terms torn rights.
Oh, torn rights. This stood out to me because it really highlights how interconnected the car's subsystems are.
Yeah, definitely.
Whenever the motor controller performs a background calibration, say it's continuously adapting to the wear of the mechanical components, it has to write that newly learned data back into the non-volatile flash memory.
Right, it has to save its work. And executing a write cycle to flash memory requires a highly stable, elevated voltage for a very specific duration.
But the 12-volt low-voltage network in an EV is, it's incredibly noisy and dynamic.
Whoa, it's chaotic.
So let's say during the exact millisecond the controller's writing to the flash, a massive high-voltage contactor snaps shut, or, the power steering pump demands a sudden surge of current.
Right.
The local 12-volt bus might experience a severe transient sag, dropping all the way down to like 6 volts.
Yeah, exactly. And if the voltage sags below the minimum threshold required by the flash controller while the write is in progress, the operation aborts.
Oh, man.
You get a torn write, the data block is left in an intermediate, completely corrupted state.
This is half-baked.
Yeah, the ones and zeros are half-written, rendering the entire block of calibration data mathematically incoherent.
Okay, so we have thermal degradation, we have ionizing radiation, and unstable electrical transients.
Right.
But the document outlines one more root cause of failure, and it involves a completely different type of chaos, which is human intervention.
Yes. System drift, caused by aftermarket repairs or manufacturing rework.
Yeah.
This is a fascinating inclusion in an ASIL D spec because it acknowledges that the mechanical reality of the car changes over time.
Right, things wear out, things break.
Imagine a technician replaces a damaged motor rotor or a position sensor.
Well, due to standard manufacturing tolerances, the new mechanical parts are never perfectly identical to the old ones, right?
Yeah.
Down to the microscopic level. So the physical 0 point of the new rotor will inherently be slightly different.
Exactly. And the standard procedure is for the technician to run a software routine called a motor commutation calibration via their diagnostic tool.
Right.
This forces the controller to learn the new physical geometry.
Okay.
But what if the technician skips this step? Or what if the routine throws an error and the car is pushed out of the bay anyway?
Then the computer still operates under the assumption that it is controlling the original mechanical hardware.
And that assumption is dangerous. The controller uses the old zero-point offset data to generate the rotating magnetic field for the new hardware.
Oh, no.
Yeah, this can result in a severe magnetic misalignment. The spec actually notes it can be up to 90 electrical degrees out of phase.
90 degrees. Wow.
The massive electromagnetic field generated by the inverter is no longer effectively pulling the rotor forward. Instead, it creates massive parasitic direct axis currents. And that energy has nowhere to go except into generating extreme heat, creating a rapid thermal runaway event in the silicon carbide power modules.
It just melts down.
Pretty much, yeah.
So because the system is under constant assault from these four distinct vectors, thermodynamics, radiation, transient electrical chaos, and human error, it needs an autonomous immune system.
It absolutely has to have one.
It needs an architecture that can detect and neutralize these discrepancies faster than the physical hardware can destroy itself.
Right. And the timeline they are working against is measured in milliseconds.
Wow.
The technical architecture defined here relies heavily on software and hardware co-diagnostics.
Okay.
And the foundational layer of this digital immune system is dual sector mirroring.
Okay, so this addresses the flash memory corruption we discussed with the thermal fatigue and the torn writes. When the controller saves its calibration data, it doesn't just write a single file. It physically partitions the flash memory and writes the data in two completely separate physical locations, right? The primary sector and the mirror sector.
Yes. And every single time the vehicle initializes, like the moment you press the brake pedal to start the car, the hardware executes a low-level bootloader self-test.
Okay.
It reads the data from both the primary and mirror sectors simultaneously. And as it reads, it runs the data through a polynomial algorithm to calculate a CRC32 checksum for each sector.
Right, the cyclic redundancy check. So it's essentially calculating a unique digital fingerprint for the block of data based on the specific arrangement of its ones and zeros.
Correct. The system compares the calculated fingerprint against the fingerprint that was saved during the last successful shutdown.
Got it.
If the primary sector's checksum fails, perhaps due to a torn write from a low battery, but the mirror sector's checksum is mathematically perfect, the system autonomously heals itself.
Oh, that's so cool.
Yeah, it literally copies the pristine mirror data over the corrupted primary sector before the motor control algorithms are even allowed to boot.
But let me pose a worst-case scenario here.
Okay.
What if a massive thermal event, or a severe voltage spike, corrupts both sectors of the flash memory? Like, what if both the primary and the mirror checksums fail the bootloader test?
Well, the architecture is strictly deterministic. It doesn't attempt to guess or extrapolate missing safety data.
Okay.
If both sectors fail, the diagnostic system triggers what is categorized as a fatal D07 fault.
D07 fault.
It initiates a hard lockout at the hardware level, refusing to close the high-voltage contactors.
Wow. So it just bricks it.
It will not start. It deliberately strands the vehicle because allowing an EV to operate with doubly corrupted motor commutation data is just an unacceptable risk.
Okay, that makes total sense. That covers the static data at startup. Well, we also talked about radiation flipping bits in the active SRAM while the car is literally flying down the highway.
Right.
How does the immune system fight an enemy that attacks while the processor is actively busy running the motor?
That is handled by the background RAM checks, or the BGCRC engine.
Okay.
And it operates completely independently of the main motor control software.
Really?
Yeah, modern microcontrollers have dedicated hardware modules specifically for this.
Oh, wow.
So during the microscopic fractions of a second when the main processor is waiting for an analog to digital conversion to finish, or is momentarily idle between calculation lips,
Right, just those tiny gaps.
this background engine sweeps through the active SRAM.
So it is continuously recalculating those CRC32 checksums on the active memory blocks entirely in the background.
Constantly. If a neutron strike flips a bit in the calibration array, the very next background sweep will catch the checksum mismatch.
And then what?
The BGCRC hardware instantly fires a non-maskable interrupt to the main processor, overriding whatever it was doing, and forces it to reload the pristine data from the protected flash memory before the corrupted value can be fed into the inverter.
So it neutralizes the radiation-induced soft error in microseconds.
Exactly.
That is incredible. But the spec actually takes it a step further, because sometimes the math is perfect, the checksums match, the memory is pristine, but the physical sensor itself is broken or drifting.
Right, hardware failure.
And this is where this system uses plausibility checks. It basically pits the mathematical model against physical reality.
Yes, and this is a brilliant layer of defense. Consider the current sensors, which measure the hundreds of amps flowing into the motor.
Okay.
Before the high-voltage system transitions into its active drive state, the controller verifies that the physical motor is at a complete standstill. The inverter switches are confirmed open.
So nothing's moving.
Right. Therefore, the laws of physics dictate that the electrical current flowing to the motor must be absolute zero.
Okay, so the computer reads the sensor data. And if the sensor is reporting anything other than zero, there's a problem.
Exactly. The specification provides strict tolerances here. If the stored offset value in the memory differs from the live sensor measurement by more than 50 milliamps while the system is confirmed idle, the software immediately flags a plausibility failure.
Oh, wow. 50 milliamps is tiny.
It is. Either the stored calibration is wrong or the physical Hall effect sensor has degraded. And similarly, it monitors mechanical plausibility.
Okay.
When it executes that zero-point learning routine we mentioned earlier, it checks if the newly learned mechanical angle falls outside a strict window of plus or minus 15 mechanical degrees from the factory baseline.
I see. So if the mechanic installed the sensor totally misaligned, the math might be correct, but the physical geometry violates the safety parameters and the system just rejects it.
Exactly.
Here's where it gets really interesting, the time limit for all of this. The specification mandates a fault-tolerant time interval, the FTTI.
Yes, the FTTI.
When a critical discrepancy is detected, the system has a maximum of 60 milliseconds to process the error, decide on a course of action, and execute a physical safe state.
60 milliseconds. From the moment a bit flips or a sensor drifts to the moment the vehicle is rendered physically safe.
That is insanely fast.
And the system employs a tiered proportional response matrix.
What does that mean?
Well, if the fault is non-critical, say a checksum error in the lookup table for the inverter coolant temperature sensor, it doesn't completely kill the propulsion.
Right, that would be dangerous too. So it initiates a degradation strategy, limp mode.
Right. It restricts the maximum torque command to 30% and clamps the vehicle speed to 40 kilometers per hour.
Okay.
It allows the driver to maneuver the car to the shoulder or a service station safely.
But if the system detects a critical error, like a corruption in the resolver absolute position data, the system response is immediate and absolute, right?
Oh, yeah. Because if the inverter fires the IGBT switches at the wrong microsecond while the rotor is spinning at highway speeds, it could generate massive negative torque.
Oh, wow.
It would physically feel like someone dropped a concrete block in front of the wheels.
Wow, okay, so to prevent that catastrophic lockup within that 60 millisecond window, the system executes an active open circuit, or AOC state.
Right.
Can you explain the physics of how an AOC actually neutralizes a spinning electric motor?
It basically comes down to isolating the magnetic fields.
Okay.
The controller instantaneously commands all 6 high-voltage switching transistors in the inverter to open, breaking the circuit.
Snap, they're open.
Exactly. By physically disconnecting the phases, it prevents the back electromotive force generated by the spinning permanent magnets from pushing current back into the battery or creating a braking torque.
Oh, I see. So the motor simply freewheels.
It just coasts. Simultaneously, the software writes a permanent non-erasable death code, DTC P0A1F, into the secure memory.
A death code?
Yeah, it locks the inverter out of any future startup attempts until specialized factory diagnostics intervene.
That is intense. But curing the error in 60 milliseconds is, a robust safety net. But the engineering philosophy outlined in the document clearly leans toward preventing the error from existing in the first place.
Absolutely.
Designing an invincible architecture at the blueprint level. Which brings us to the DFMEA, the design failure mode in effects analysis.
Yeah, and this is where we see the physical manifestations of that engineered paranoia we were talking about.
Yeah.
Let's look at the memory silicon itself. To meet ASIL D, standard flash memory just isn't enough.
Right.
The hardware specification mandates SEC, ECC across all safety-critical memory domains.
Okay, that's a mouthful. That is single error correction, double error detection, error correcting code.
Exactly.
So at the deepest logic gate level, every 32-bit word of calibration data is paired with an additional set of parity bits.
Right.
And the hardware logic gates automatically evaluate these bits during every single read operation.
And if a single bit has been flipped by radiation, the logic gates use the parity data to mathematically reconstruct the correct bit and fix it on the fly.
Oh,
Yeah, without the main processor ever knowing it even happened. It can silently correct single errors and reliably detect if 2 bits in the same word are corrupted, which would trigger a hard fault.
That's amazing.
Yeah.
And to protect against rogue software, say a bug in the infotainment system, somehow trying to write data to the motor controller, they encapsulate the calibration data inside a memory protection unit, an MPU.
Yeah, the MPU. The MPU hardware partitions the memory map. So the calibration sector is designated strictly as a read-only vault.
Okay.
It is physically impossible for standard application code to write to those addresses.
Really?
Yeah. To alter that data, the processor must be in a highly privileged supervisor mode, and it must present a specific cryptographic safety key to the MPU just milliseconds before the write command.
Wow, so it's locked down tight.
Very tight.
That handles the logical protection. But what about the physical degradation? The thermal tunneling we talked about, the silicon lattice breaking down under 125-degree heat.
Right. To combat physical flash wear out, the design employs a complex wear leveling algorithm.
Okay, how does that work?
Well, writing and erasing flash memory physically damages the oxide layer. If the system constantly overwrote the exact same physical memory addresses every time it updated a calibration parameter, those specific cells would just burn out rapidly.
Ah, I see. So the wear leveling algorithm abstracts the logical addresses from the physical addresses.
Exactly. It systematically rotates the data, spreading the erase-write cycles evenly across the entire surface of the flash chip.
So by distributing the physical stress, the specification actually guarantees the flash memory will survive over 100,000 erase-write cycles.
Yeah.
And crucially, it guarantees data retention for 20 years at a continuous roasting 125 degrees Celsius.
It's impressive.
It really is.
Yeah.
Moving beyond the microchips, the DFMEA also dictates mechanical prevention. To stop the physical drift that causes those 90-degree magnetic misalignments, they utilize mechanical poka-yoke.
Right, poka-yoke. It's a Japanese manufacturing concept that translates to mistake-proofing.
Okay.
In this context, it means designing the physical hardware so that it is geometrically impossible to assemble or shift out of alignment.
So it's basically like child-proofing a house, but for violent physical forces.
That's a great way to put it, yeah. The specification details the mechanical interface between the resolver rotor, the sensor target, and the motor's main drive shaft.
Right.
They don't just rely on a friction fit or a simple set screw.
No, the blueprints dictate dedicated asymmetrical keyways and interlocking geometric steps machined directly into the steel.
Right.
And they mechanically lock the rotor's dynamic run-out tolerance, which is the maximum allowed off-center wobble during high-speed rotation, to an incredibly tight measurement of less than or equal to 0.05 millimeters.
0.05 millimeters. That's basically nothing.
Right. By enforcing a 0.05 millimeter tolerance and physically keying the shaft, you completely eliminate the physical channel for the sensor to slip or vibrate out of its calibrated 0 point.
Wow.
It is geometrically blocked from failing.
Geometrically blocked. I love that. And returning to the radiation issue, the alpha particles coming from the chip packaging itself. The DFMEA attacks this at the material science supply chain level.
Oh, this is fascinating. If we connect this to the bigger picture, the engineers actually regulate the radioactivity of the plastic resin used to encapsulate the silicon.
That is just next-level paranoia.
It really is. The spec mandates the use of ultra-low alpha emission packaging materials.
Okay.
The resin manufacturers have to implement intensive purification processes to strip out naturally occurring radioactive isotopes from the epoxy.
Wow.
The final material must emit less than or equal to 0.0010 counts per hour per square centimeter.
That's incredibly low.
Yeah, it is about starving the failure mode of its energy source. And the specification also addresses the immense electrical noise inside the inverter. Modern EVs use silicon carbide transistors that switch hundreds of amps at 800 volts in a matter of nanoseconds.
Which is violent.
Right. The electromagnetic interference generated by that switching is violent enough to induce false voltages on the low-voltage communication lines.
Exactly. It creates a massive common mode transient voltage spike.
Okay.
To prevent this noise from scrambling the digital data traveling between the microcontroller and the high-voltage gate drivers, the design uses high-speed optical and capacitive isolators.
So instead of sending an electrical voltage across a continuous copper trace, the isolator converts the digital signal into a pulse of light.
Right.
Shoots it across a microscopic physical air gap within the chip, and converts it back to an electrical signal on the other side.
Yes, because electromagnetic interference cannot alter a photon.
Oh, wow. That's brilliant.
The specification demands a common mode transient immunity, or CMTI, of greater than 100 kilovolts per microsecond. It ensures that no matter how violent the high-voltage switching transients get, the low-voltage memory and communication lines remain utterly isolated and protected.
So we have an invincible blueprint. The silicon is purified, the architecture is redundant, the mechanics are locked down.
Right.
But an invincible blueprint is entirely compromised if the factory assembly line introduces a flaw.
Oh, completely. Which brings us to the PFMEA, the process failure mode and effects analysis.
Yeah.
The manufacturing controls detailed here are arguably more rigorous than the design phase. The factory floor is treated as a high-stakes deterministic environment.
So the first line of defense is the MES auto-calibration lockout. The factory's central computer network, the manufacturing execution system, is digitally interlocked with the calibration robots on the assembly line.
Yes. When a fully assembled motor reaches the end-of-line test station, the robot spins it under a precise microload to establish its unique physical zero point and sensor offsets.
Which is the critical baseline data we've been talking about.
Exactly. If the learned parameters fall outside an incredibly narrow statistical window, perhaps a bearing is slightly out of spec, causing a minute drag, the localized robot flags a failure.
Okay.
But it doesn't just display a red light for a human operator to potentially ignore.
Right.
The MES takes over. It physically blocks the work order in the central database.
So it just stops everything.
It refuses to generate the final serial number or print the barcode label. The pallet conveyance system will literally physically divert that unit to a quarantine zone.
Wow.
A human operator cannot override the system to push a mathematically flawed unit out the door.
That is a hard stop. Next, the factory performs automated current calibration. The testing machines inject ultra-precise laboratory-grade currents directly into the motor windings, sweeping through 10 amps, 50 amps, and 100 amps.
Right, and this maps the exact nonlinearities and resistance variances of the specific current sensors installed on that unique motor. The robotic system calculates the compensation curves and flashes those bespoke corrections directly into the SEC die-protected memory.
But I think the most staggering process control in the PFMEA is the physical inspection. The 100% 3D X-ray vision requirements.
Oh, yeah.
I mean, I was in awe reading this. They don't just rely on electrical testing to ensure the microchips are attached properly. Every single main microchip's BGA, the ball grid array of solder joints underneath the chip, is scanned with an automated X-ray inspection machine.
Right. They are using 3D laminography to look deep inside the microscopic solder balls connecting the chip to the printed circuit board.
That's insane.
And they are looking for voiding, which are microscopic air bubbles trapped inside the molten solder during the reflow oven process.
Right. And the spec defines limits that seem bordering on obsessive. The total void area across all joints must be less than or equal to 5%.
Right.
And no single individual solder bump can contain a void larger than 1% of its volume. Why is a 1% air bubble inside a microscopic solder joint a critical safety threat?
Well, it's because of the application environment. An electric motor running at 12,000 RPM generates intense, continuous, high-frequency vibration.
Okay.
In material science, a void inside a crystalline structure like solder acts as a stress concentrator. Over millions of vibrational cycles, the mechanical stress focuses on the edge of that tiny air bubble, initiating a microcrack.
Oh, I see. So as the crack propagates through the solder joint over months of driving, the physical connection degrades.
And as the physical connection degrades, the electrical resistance of that specific solder joint increases, perhaps just by a few millions.
Right.
But if that specific solder joint is the pathway for the sensitive analog signal coming from the current sensor shunt resistor, a change in resistance completely alters the voltage drop.
So the analog to digital converter reads that altered voltage, interprets it as a massive surge in motor current, and feeds that lie to the control algorithm.
Exactly.
The calibration is suddenly corrupted by physics, without a single byte of flash memory actually failing.
Exactly. The 3D X-ray limits ensure the structural integrity required to prevent vibration-induced resistance drift over the 20-year lifespan of the vehicle.
Wow.
And as a final factory safeguard, before the unit is boxed, it undergoes readback verification.
Right. Every single byte of data written to the drive's memory during the assembly process is read back out by the tester.
Yeah.
The data is hashed using a SATA 256 cryptographic algorithm and compare it against a master golden database stored on the factory server.
Right.
And if a single 1 or 0 was flipped by electrical noise during the factory programming, the hashes won't match and the unit is quarantined.
They've designed an impenetrable system on paper, and they've built it with draconian precision in the factory. But the engineering process demands one final phase.
Right.
They have to prove that all the math, the error-correcting codes, and the material science actually hold up in the brutal physical reality of the real world.
The DVP&R design verification plan a report. This is the production validation phase, which is essentially a trial by fire.
Oh, yeah.
They subject production intent hardware to absolute torture.
Whoa.
And the first test detailed is the combined vibration and thermal shock test, colloquially known as the shake and bake.
The parameters are punishing.
Yeah.
The system is placed in an environmental chamber and subjected to 1,000 continuous cycles, swinging rapidly from -40 degrees to positive 125 degrees Celsius to induce maximum thermal expansion and contraction stress on the PCB.
Right. And while the boards are warping from the thermal shock, they are bolted to a shaker table, violently vibrating the system at 35 meters per second squared across all 3 spatial axes, while the controller is fully powered and operating.
Yeah, the test is designed to accelerate years of mechanical and thermal abuse into a matter of weeks.
Wow.
And the passing criteria are binary and absolute. Following the 1,000 cycles, the memory checksums are queried.
Right.
Not a single bit can have flipped or leaked from the flash memory.
And then they take it further with destructive physical analysis. They literally dissect the hardware.
They do. They use precision saws to cross-section the circuit boards, polishing the edges so they can examine those specific BGA solder joints under high-powered electron microscopes.
Oh, man.
The requirement is zero evidence of microcracking propagating from any voids. Furthermore, they measure the electrical resistance across the joints, and it cannot have increased by more than 1.2 milliohms compared to its pre-test baseline.
That is so rigorous.
Yeah.
Next is the brownout test, which specifically targets the torn right vulnerability we discussed.
Right.
The engineers place the controller in a loop of 10,000 continuous calibration memory saves.
And right in the middle of a write cycle, they intentionally drop the primary 12-volt supply down to 6 volts for exactly 20 milliseconds.
So they are actively trying to starve the flash memory controller of the voltage it needs to finish writing the block.
Yes. And the architecture must survive this by relying entirely on its local hardware design. The backup capacitors clustered around the microcontroller must hold enough residual energy to maintain the internal voltage rails above the critical threshold, just long enough for the flash controller to gracefully finalize the write cycle and commit the checksum, preventing the data corruption.
Wow. But the most intense validation is the 12,000 RPM fault injection test. This is where they test the 60 millisecond FTTI response time under absolute worst-case physical conditions.
This raises an important question, right? What happens at top speed?
Right.
They mount the complete inverter and motor assembly on a highly instrumented hardware-in-the-loop dynamometer test bench.
The HIL bench?
Yeah. They run the motor up to its maximum speed of 12,000 RPM, placing it under full mechanical load. The system is pushing massive power, operating at the very edge of its performance envelope.
And while it's screaming at 12,000 RPM, the engineers use a debug interface to intentionally inject a bit flip directly into the active SRAM holding the resolver angle data. So they instantly trick the motor control algorithm into thinking the physical rotor just violently twisted 45 degrees out of phase.
Yeah, and in a fraction of a microsecond, the algorithm's math calculates a massive positional error.
Okay.
If left unchecked, the PI controllers would immediately output maximum voltage vectors to try and correct the error, which would inject catastrophic negative torque into the spinning mechanical driveline.
But the digital immune system intervenes.
It has to. The background RAM check, or the plausibility algorithms, must catch the discrepancy, fire the interrupt, and command the active open circuit shutdown.
Right. And the results of this specific test define the success of the ASIL D rating. The dynamometer sensors measure the physical outputs during the shutdown event.
Yeah.
The torque ripple, the violent mechanical jerk experienced by the driveline before the IGBT switch is open, must be clamped to less than 5 Newton meters.
Furthermore, opening the switches at maximum load creates a massive inductive voltage spike. The hardware must absorb and clamp that transient to under 720 volts to protect the silicon carbide modules from just blowing apart.
Wow.
And the permanent magnets on the rotor must survive the transient fields without demagnetizing.
And crucially, the system must transition the mechanical driveline into a safe, freewheeling coast. The wheels cannot lock up.
Right.
And all of that detection, processing, and high-voltage isolation must complete in under 60 milliseconds.
To reliably execute that sequence at 12,000 RPM requires an architectural harmony between the software logic and the physical hardware that borders on the miraculous.
So what does this all mean? When you're driving down the highway, listening to music, experiencing the smooth, silent acceleration of a modern EV, that profound feeling of safety isn't just the result of a heavy steel chassis or airbags.
No, not at all.
It is a result of thousands of invisible sub-millisecond battles happening every single second inside the silicon. Battles against extreme thermodynamics, the decay of radioactive isotopes, and chaotic electrical transients.
Yeah. The engineered paranoia meticulously documented in this specification is the invisible safety net you rely on, entirely hidden beneath the surface of the user experience.
It truly is.
Uh,
But before we wrap up this deep dive, there was one detail buried in the final appendices of the source document that I want to bring up.
oh, yeah.
The engineering team offers a final tool to the integrators. They offer to provide a Python simulation model.
Yes, I noted that as well. A software model designed to simulate the microscopic charge leakage in the flash memory arrays and the transient voltage drops across the PCB traces in absolute worst-case environmental scenarios.
Right. They want to mathematically simulate the exact rate at which electrons will tunnel out of microscopic silicon dioxide buckets under specific heat loads over a 20-year timeline, just to define the ultimate boundaries of the safety margin. And this gave me a profound thought to leave you with. If the hardware physics have become so incredibly microscopic, so interconnected, and the required safety margins are so unimaginably tight that we have to rely on software simulations to predict quantum-level decay under cosmic radiation over decades.
It raises the question, are we approaching a threshold where human engineers can no longer intuitively understand or manually calculate the physical limits of their own creations?
Exactly. As our machines become hyper-complex, does our physical real-world safety on the highway rely entirely on how accurately our algorithms can hallucinate the physical future of quantum decay? It's a wild paradigm shift in engineering to consider.
It really is.
Something to mull over the next time you press the accelerator.